Okay, hi everyone, and welcome to Robotics Fighting Sight Loss, which is our 6th event in the Festival of Disruptive Thinking series hosted by the Entrepreneurship Institute. My name is Annabelle, and it's my pleasure to be moderating this event and to welcome you all here today. My colleague Nina is also here, and she'll be posting some additional information in the chat box. For those who aren't familiar with the Entrepreneurship Institute, we support students, staff, and alumni at King's to develop their entrepreneurial mindset. We believe that everyone can be entrepreneurial and that entrepreneurial people can make the world a better place by solving problems and creating a smarter, more equal, and sustainable future. This week's festival showcases disruptive thinking, which is the ability to question and challenge the status quo of established systems to progress new ideas and ways of thinking. We're delighted that Christos Bergeles is joining us today to share his experience of being disruptive. Christos is a reader in surgical robotics within the School of Biomedical Engineering and Imaging Sciences. He is leading the Robotics and Vision and Medicine Lab and has come to talk to us today about their work and how they're pushing the boundaries of traditional treatment through innovation with surgical robotics. Just before we get started, a few bits of housekeeping. This event is being recorded, so please mute your mics and turn your camera off if you prefer. There'll also be some time for a Q&A at the end of the presentation, so feel free to drop any questions into the chat or save them until the end. And that's it, we're ready to go, so whenever you're ready, Christos.
Thank you very much for the introduction. I'm happy to be here. Have a dual hat, so to speak, one as an academic where we are developing this technology, but I'm also very happy to be part of King's 20, the Health Innovators cohort of the Entrepreneurship Institute. So what I will talk about is not only some of the scientific aspects that we do, but how do we try to take this closer to the clinic and what do we learn in the process of doing that. So my lab in general, what we do is we enhance surgical dexterity in confined spaces. So we are creating microscopic instrumentation, robotic instrumentation, and the associated computer vision algorithms that allow us to give increased dexterity to clinicians, both in terms of like what they could do by manipulating instruments, but also mental dexterity. So what can they see more in images that they cannot otherwise perceive? So the lab has two big pillars in terms of its focus. It has vitreoretinal surgery, which we have been working on now for almost 7 years. This is a highly collaborative project. It involves a multitude of specialists like machine learning engineers and mechatronics engineers and systems engineers, quality management experts, and of course, clinical input, without which we cannot have projects that are anchored to clinical applications. And the second big pillar of the lab is neurosurgery, which is something that's more nascent. We now establish very good clinical collaborations, and we're starting building our prototypes. And we also are looking how we can transfer learnings from the vitreoretinal surgery domain, which is like more microscopic and more, a hollow cavity to neurosurgery and vice versa. So I will be talking today about what we do in the domain of sight saving. This is what we call vitreoretinal surgery. It is essentially surgery that is taking place in the back of the eye, inside the eye and in the back of the eye where the retina resides. This is the current state of the robotic system. It aims to show you how we are using the facilities of the Surgical and Intervention Engineering Department at King's College London. We have a fully kitted mock operating room. Soon we will get permission for cadaveric human trials. And we have the surgical beds, the microscopes, the lights, the most of the instrumentation you would find in an operating room. And we are trying to replicate these conditions, these surgical room conditions, to understand how our device will fit within an operating room workflow. We need to be able to understand dimensional constraints, dexterity constraints, how different equipment work with each other in order to ultimately identify the problems and solve the problems that are most relevant to taking this technology a step further. This is one of the unique capabilities that we have King's among internationally, and it does allows us to bridge this gap between what we do in an academic setting, which is occasionally simplifying problems, and what you would do in a complete clinical setting where even the smallest detail can end up being a very big engineering challenge. I will talk about VIPER. VIPER stands for Versatile Intraocular Precision Enhancing Robot. And this is really the robot we are developing, a flexible robot that moves inside the eye. It is suspended here by this bigger manipulator, and this end of the tip here, this would go inside the eye, and then it would flex in order to achieve different configurations and acting like a dexterous wrist within the eye. This project has been generously funded by a variety of sources, primarily the National Institutes for Health Research, which is a funding organization that bridges innovation like pure scientific research with the capability of clinical translation. So they are looking for applications that would benefit the NHS and applications that have a commercialization strategy to back them up. So it is the sweet spot in which we would like to operate, and definitely we are very, very happy for their support and grateful. So after years of research and after years of talking to clinicians and collaborating on a variety of projects, the lab has come up with a pipeline which we're trying to implement when we come up with new projects, when we come up with new ideas, because we don't want just to have ideas that are cool and could generate like great scientific publications. Of course, we have those as well, but we want to see the endpoint. We want to have an anchor on patient benefits that is motivating us and driving the innovation towards a direction. Like this sort of pipeline gives us the bearing for the projects or where we want to be going to. So we always engage with key opinion leaders. Like now that the lab is more mature, we are even earlier and earlier engaging with them. We are discussing the unmet needs. We go to the operating rooms. We really understand what is the problem that needs to be solved. Normally, academic labs go and say, okay, we have a great solution. What is your problem? What problem can you solve with our solution? We have been doing that as well, and sometimes it works, sometimes not. But really, when you talk more and more with these key opinion people, the more you understand exactly what the problem is to be solved, and then you try to see whether you have the technology to solve the problem, or whether you want to carry out innovation in order to create new intellectual property, differentiate from your competitors, and create something that is really fit for purpose. And after these two processes take place, and of course everything is iterative, then we go to create the proof of concept, and we have like the clear path of what should we publish, what should we protect with patent applications, what is really our unique selling point, why would somebody prefer our solution, be that algorithmic, be that mechanical, from the state of the art or from the commercial competition. So what really sets us apart? And this is normal in the academic process, but what we try to add is a gist of commercialization strategy, having a sense of health economics, addressable markets, potential financial models. And this is really now what we're working with the Entrepreneurship Institute in fine-tuning. How can we take our technology, our algorithms, our devices, our prototypes to the next step? And yeah, so this I think is what is the make or break after any sort of academic technology is developed, because maybe the technology is too expensive, maybe the technology doesn't have a market. And this I think is something we have consolidated and really try to do now iteratively, both as we develop our grants and as we work on our projects. That said, in the context of eye surgery, the disease we are aiming to fight is age-related macular degeneration. Age-related macular degeneration is manifesting as a gradual loss of central vision. And what this means is we lose our ability to read, our ability to recognize faces, our ability to focus on the task at hand, while we retain the peripheral vision, which allows us to navigate in space and walk. Now, obviously, because most of the stuff we do on a day-to-day basis require this central part of vision to be intact, AMD has a huge societal impact. And of course, a huge economic impact as well. If you imagine in the UK that 2 million people suffer from sight loss, then almost half of it is from age-related macular degeneration, and the number rises to 200 million worldwide, so it's a huge problem. There is prevalence of 5% of people over 65 years old, and the disease comes in two forms. In a wet form, which can be controlled with injections of drugs inside the eye that stop the progression of the generation of new vessels, and in a dry form, which doesn't have a cure apart from new regenerative therapies that are now under development. But of course, 90% is this dry AMD, which doesn't have the cure yet. And even if there is a cure, there is a big cost that is associated with treating it timely, with treating it precisely. And the problem is that even when these new therapies come, you want to deliver them exactly where they're supposed to go. So you need a delivery mechanism that goes inside the eye and says, okay, the therapy should go at this specific location for this duration of time with a stable hand. And this parallel problem of therapy and delivery is what we are aiming to tackle. We have strong collaborators in the biology domain from Moorfields Eye Hospital and UCL, and we are working on the delivery domain. And we hope to marry the two approaches into one solution as the years go by and the projects mature. To give you an understanding of why this sort of interventions are currently impossible is imagine this scenario. This is how eye surgery takes place. The surgeon looks through a microscope. They're manipulating two instruments. And the instrument here on the right, this is a very, very tiny injector. They're trying to visualize where they are injecting. This crosshair is giving you optical coherence tomography images. You can't see anything. There is these shadows. These are the shadows of the metallic tool. This is like ultrasound, but with light. And of course, metal reflects, so you see the shadows. You really can't realize, I mean, okay, there is a bolus here. This is the injection happening. This is the current state of the art. And then, oh, okay, you kind of move somewhere else here. Okay, wow, there is an injection. This is really therapy that has been delivered. So it is taking place in a very hand wavy fashion. That hand tremor is very high. Also, you can't see very well. So we have this dual problem of imaging and of surgical dexterity. And in this specific case, the therapy just is injected at this green layer. This is a natural cleavage plane. It's like you're going through the eye and you're reaching the other end, and then you feel like a stop. And then you have this haptic feedback manually and say, okay, now I'm going to inject. But if you want to go in between this layer, this is the retina of the human eye. This is where vision takes place. This has a tremendous amount of details and neurons and cells and therapy and nutrient providers, and it is as thick as the human hair. So imagine needing to go within the human hair and operating inside the human hair. We're talking about 5 to 10 micrometers of precision, and you want to do that under excellent visualization capabilities. So this is very hard, and this is where we come in with the robotic solutions. Now, schematically, it's a little bit easier to understand. This is the human eye. What you see here as this tiny, tiny dimple, this is where macular degeneration happens. This is the point of highest vision within the eye. This is where 99% of sight takes place. And these layers here, these are just a few of the layers that this tiny, tiny part has. This is the human retina. So you have here cells that are responsible for that. These are the ganglion cells, and then you have photoreceptor cells, and then you have nerve cells, and at the end you have nutrient cells. So in this tiny human hair-like structure, you have packed at least 7 different layers of cells, each of which has a specific functionality. So now, if I want to go and change the photoreceptor cells, I need to have a very good precision in how to do that. And that's where robotics comes in. Now, in the process of developing those robotic systems, we engage with patients as well. We're trying to explain together with patients what we are doing, why what we're doing is important, and we need to cast it in a way that it is understandable, and also to get feedback back from patients so that we can develop the technology so that it is acceptable, so that it is more fit for purpose. We're doing consultation groups, and we're trying to gather these viewpoints and use these viewpoints to make the research go further. One of the nice things we have done is we are creating infographics. So we're capturing the patient's opinions and all these consultations into nice looking pictures that also highlight some of the misconceptions. For example, I know in this specific, you wouldn't see it, but there are, for example, what can the robots cancel appointments, or what happens with sort of the life cycle of robots, and all these details help us inform our future applications and the directions that the technology can be developed further in. So in this specific case of eye surgery, we consulted with clinicians. We know what we need to do. We need to operate in confined spaces. We need to have full dexterity at the tip. We want to be very, very small. We're talking like, 600 micrometers, 700 micrometers, and we need to be able to deliver therapies and also suck out potentially harmful pathogens. The technology we're using in the lab is based on what we call concentric tubes. These are pre-curved super elastic tubes, and when you put one tube inside the other, then they conform to a mutual shape. And if I grab tube 1 from the back here and I rotate it, then I can rotate the entire assembly. If I rotate only tube 3 or I reset it, then I have control only over the tip of the assembly. So this is called a continuum robot. And it allows us in a very confined space to have high dexterity at the tip while being relatively immobile at the entry point in the eye. So as a technology, these small robots have the highest curvature potential, so the highest dexterity potential, and the smallest diameters. So they are very good for confined spaces. Of course, now we want to answer scientific questions like how do we design these robots? How do we model these robots? How do we telemanipulate them? In other words, how does a clinician sit in a console and move these robots around? And how can we manufacture them and add sensors on them? So even though we have the idea and the system requirements, the surgical requirements, there are a lot of scientific questions that need to be answered before this technology becomes mature. We need to keep an eye on what we publish and what we patent. And we started early with prototypes based on hobby electronics and to show proof of concept and understand whether we can have these small robots operating inside the eye. We developed algorithms for reachability. This is just the capacity to reach a specific point with these flexible robots. This is a robot that would go inside the brain, for example. We have tried to increase the performance of such algorithms so they can be used in an interactive setting so that the surgeon could sit at the console and use these robotic systems and they would respond very quickly. How do we control them? How can we predict their behavior looking in the future? Are they going to encounter any sort of instability? What forces may they apply in the future? And factor this all in control. And of course, patenting so that we can have a case for commercialization. We're developing robots and we are keeping copyright of algorithms that allows us to create these instruments that in confined spaces can be very, very dexterous. We have a pipeline to design these robots, and this is, let's say, in-house capabilities. And we use anatomical volumes acquired by MRI. We are highlighting the regions that we would like to reach. Then we define the surgical tasks that we want to achieve, and they could be reach a specific point under any permissible orientation or reach a variety of points within the anatomy of interest. And these surgical tasks and constraints, together with a robot model and a mathematical framework, they give us the design of those tubes. So how long should they be? How curved should they be? How much do I need to move them and insert them in order to reach the surgical task that we have at hand? Of course, we also have the telemanipulation capabilities. One of the strengths in the team is doing the inverse kinematics, so controlling the robot to go where we want. And what you can see here is depending on the fidelity of the models that you're using, you can either track very, very closely the blue target and follow it, or you will have like a very jittery approach because your mathematics are just not solving well enough. And of course, nothing is really valid without having proper simulations and proper experiments to understand how things are performing. So we evaluate these kinematic models with actual experimentation. These are the sort of surgical instruments in the dimensions that we larger dimensions to be able to do the validation. And we are predicting dynamic instabilities and interaction with tissue and so on. So there's a lot of mathematics and everything going behind it. And what you can see in this is gradually as we are letting our algorithms run, we are increasing what you see as a gray territory, and this is the territory within the eye where these robots can operate like micrometer wrists. So these optimization algorithms, you will let them run, then they are becoming more and more capable of performing a task at hand. And this is an example of how the instrument would work behind the eye. So basically there are multiple generations of robots with specific curvatures and lengths that are being evaluated and optimized in order to reach the specific point under any orientation I want. So with these algorithms in mind, we are able to create these dexterous instruments now, and we take it to the next step, which is to implement them on top of a mechatronic system. This is how our system looked 2 years ago. I don't have a better video. This is one thing we discussed in the team. We have a medical grade coarse manipulator from KUKA Robotics, and then we are attaching our robotic system on top. We then have a model of attaching tools, and these tools will be disposable. This is some of where the commercialization ideas come in. And we have a programmatic approach, either automated or co-manipulated to reach the point in the eye where the instrument will go in. This is the picture inside the eye. This flexible instrument is extending. It will reach the vessel, and this is like how it looks from outside. And we can do vessel targeting at this stage. So these vessels here are less than 1 millimeter thick. They are painted with a very, very fine brush, and we can move along them and target their middle, which shows that we can do what we would like. The other thing that's interesting and ties well with what our mission is through the Entrepreneurship Institute is we need to define marketing strategies for what we are developing so that we can bring patient benefit. And we are working together with the translation office of King's, and also with external partners to understand what can we commercialize and how we can also de-risk our commercialization approach. So, for example, is our robot needs some software to run. It needs to track locations inside the eye so that it could stabilize itself. Can we have this software as a standalone product? What would it benefit? Who would be our potential purchaser? Would it be microscope companies? Would it be hospitals? Would it be an add-on to existing microscopes, and so on? And on the other end of the spectrum, we have the complete system. It would work with any sort of approved therapy. We're exploring partnerships with companies that develop those therapies, and we are doing health economics analysis to understand, well, what can the system cost be so that the NHS saves money? Because if we build a system that costs $1 million and then there is no way for the NHS to recover these costs, then it won't be uptaken in a setting like the UK one. And of course, you need different strategies depending on which healthcare system you're looking at. And you can also have a middle ground, or you must have a middle ground, because if you wait all the way until the end, until you have the super product, then maybe it's too late. So we're trying to find a sweet spot somewhere in between where we have not all the functionality, but at least something that some people will buy or some hospitals will buy and say, okay, well, this is something that we can use, and maybe a donor buys it, or something that allows us to get a foothold in the market. For example, having a robot that autonomously illuminates a surface, and then you can maybe free up the surgeon's hand that holds the light, and they can do something more advanced. So this is how the system looks like right now. It is we have ideas of a company. We call it Revitalize. It's a little bit hard to read, but yeah, so maybe branding needs some working there. But I like the tagline, re-engineering human sight, because that's what we're trying to do. We're using engineering to help people with sight loss. We're mentored, as I said, by the King's Entrepreneurship Institute. And right now, the state of the project is it has a research pillar and it has a development pillar. So we are developing this technology under a quality management system. Again, King's is one of the few places that have the support to develop medical devices under a quality management system. We also have a clean room that we are developing, a clean room facility to create up to class 3 medical devices. And this is an exciting journey because as academics, we tend to brush off a lot of the details. And in a paper, it would be like, see the side notes. But when you are developing under a quality management system, every detail needs to be well documented, well reasoned. It has to be risk assessed. And this is definitely a training process for us and a lot of documentation to generate. But it puts us in a mindset, which is how like a spin out would work. So we are actually funded within an academic setting to do groundwork that a company would do. So when we do spin out, we will be at a much better state to seek investment. And that's what I had to share with you. I think I went too fast looking at the time, or am I okay?
Yeah, that's great. That's
All
great.
right, thank you very much. I don't have a watch here, so I couldn't pace myself.
No, it's perfect timing. We've got like a good amount of time for questions as well.
Thank you
So
very much.
thank you so much, Christoph. That was really interesting and just so clever. I think sight is something that I probably take for granted. So I think it's really amazing that you're creating a solution for this. So yeah, if we open up the floor to any questions, so you can either pop one in the chat box or unmute your mic and ask Christoph yourself.
Oh, there are a few questions in the chat. Should I be reading them?
Yeah, Fatma has asked why eyesight and what has been the response of clinician towards this innovation?
That's a very good question. So it's a little bit of serendipity in the sense that when I started my PhD, the project I was involved in had to do with eyesight and drug delivery. So I kind of liked a lot the clinical domain and the challenges it has, both in terms of biology and in terms of engineering. So I kind of stayed with it. Now, why eyesight in my PhD? Well, that's another serendipity. So sometimes it's just luck that brings you in a domain, and then you just stay with it. And the response of the clinicians, I would say, depends on who you talk to. And this is a very important thing because it's a question like you would ask, what would you need a robot to do for you? And then it's hard to, for anybody, it's like if you ask any practitioner, what can't you do right now? A reflex answer is I can do everything, because if the answer is I can't do everything, then this implies something also about their capabilities. So most of the clinicians say I can do everything I need right now. And then you need to dive a little bit deeper. Okay, what could you do better? And then suddenly you have these discussions, and this is what leads to the development of these robotic instruments. And we are very, very, very thankful. We are collaborating with Lyndon Da Cruz, who is from Moorfields and UCL, and they are making these therapies with Pete Coffey, so they have a real need. But of course, you need to identify the collaborators that will help you drive the innovation forward. You are muted, Annabelle.
Oh, sorry. Thank you. I have quite a broad question. Do you think there'd ever be a world where all surgeries are done by robots, or would you always need like medical staff? Would that go hand in hand?
Yeah, there will be a world where surgeries are handled just by robots. You go in an a la carte fashion. Now, that will not be in our lifetimes, I gather. But I do think in the lifetime of our children, yes, I do believe that. And I mean, if you think where we were 30 years ago or 40 years, like a generation ago, which was absolutely nowhere, and where we are now, it was just laparoscopy, which was just starting, and now you have robots. Then I think we can extrapolate, and I believe there will be automation within our lifetime, maybe partial automation, but ultimately, yeah, it would be full automation. And right now there are surgeries that are fully automated. For example, there are neurosurgeries that, like CyberKnife, it detects it has like a plan of where the tumor is, and it zaps the tumor. It just moves like a proton beam. This is fully automated. There is staff to make sure that everything goes well, and I think this will always be there. But it's automated. Similar in cataract surgery, it's automated. But there is staff to make sure that things go well, like an overseer. So this won't go away, but most of the surgeries will be, yeah, I think automated, definitely.
Wow. It's crazy to think about like how far it could go in the future. We've got a question from Arian, who said, how far is this technology from real life implements, and what is the biggest technical hurdle that you have had to clear?
Well, the goal is to do a validation of the minimum viable product in 3 years. So it's within grasp. So now we have a specific timeline, funding deliverables, and milestones we need to meet. So that's of course not the full technology, but I think after we do that, then it's not a big leap to go to the next level. The hurdles now, this is a very good question because they keep appearing. So I don't know what the biggest hurdle will be. No, it's with this in the level of detail that we need to to work in to create a medical device, even the smallest detail, when you look into it, it's a can of worms that ends up being a big technical hurdle. So I don't really know. I don't. This is going to be a surprise. For example, just positioning the robot close to the eye, which is one of the things that in an academic paper we're like, and by the way, somebody will position next to the eye. In a technical setting, it's actually very challenging, but we didn't know it until we had to do it 10 times. We see, okay, wait a minute, this is actually a separate research and development project. So yeah, it's full of surprises.
I think relating to that, we've got two more questions. Is, do you have an approximate time frame for when it will go to market? And just to, someone wanted you to clarify, are these robots still under development?
Yeah, they're definitely under development still. So there are other systems that are also, like from other laboratories and companies that are under development. I think it's, yeah, most of the stages are similar, like, they're going to preclinical or they have a prototype. I think in the next 3-4 years, we will see these robots entering the market. There is a robot that is in the market already. It's a Precise company from the Netherlands. If you have 300,000 to spare, you can buy it. So it's a matter of cost saving afterwards, really making sure that there are benefits, and how do you prove these benefits? You might need a health technology assessment, or NICE might need to come in and evaluate the technology. So there is a process after that, but yeah, it is still being considered.
Another question is, would this robot be considered part of soft robotics?
Yeah, I mean, depends. If I'm writing a grant, it is. If I'm doing a commercialization spin, it's not. So the tubes are compliant, and you can fabricate it so that they exhibit softness with regard, which is relative to the tissue you're manipulating. So yes, you could etch material out so that they have a certain compliance and softness, but they are not soft in the malleable sense that is used in the academic setting. We have other robots that are completely soft, and they would just like grow within the anatomy. Yeah, so I wouldn't consider these robots soft. They are stiff but compliant.
Okay, great. We're getting lots of questions coming through. So next one is, how much training would be required to operate these robots?
Well, that's a good question. I don't know, but the thing is, if operating the system after it's being set up requires anything more than half an hour, I think then it becomes problematic. Setting up the system, yes, this would require training, and mastering the system will require training, but it has to be very intuitive in using it. Otherwise, it would be hard to make people to adopt it. Yeah, I mean, this probably we need to read a little bit how much training do other systems require, and then we will have our benchmark.
Okay, next is, how widespread is the idea to use flexible tubes inside each other?
I mean, it is known. There are other labs that are working on this and have initiated it. It's not our. We didn't write the first paper, let's say, on it, but. Yeah, I'd say it's not the most widespread idea, but people in the domain know about
it. Next question, can we apply these robots for subretinal injections?
Yeah, that's a very, very good question. The short answer is yes. There is nothing stopping you, but then the clinical requirement question is, do you need a robot to do subretinal injections? And yeah, there are studies that show that yes, you can do them with robots, but whether you need the robot or not, that's a question, and this you need a proper assessment to evaluate. Whereas inside the retina, this definitely you cannot do by hand.
We've got another question that says, has a cost assessment been considered already for the robots to be supplied yet? And if so, how much does the system cost to set up?
Yeah, so this is we are exploring it right now. We're doing a health economic study. This is not going to tell us the cost of the robot, but I think it will give us an understanding of how much can the cost of the robot be, and then we might need to work backwards. and understand our margins. And then maybe this whole thing is mute and there is no cost model that makes sense. But I think that's not going to be the case.
Someone's asked that they imagine that controlling the flexible tubes is quite difficult, and do you develop a special user interface to control the tubes?
So this is a good question again. I mean, it's a very good question. We don't have a straight answer. We're evaluating two different approaches. The one is you're holding a stylus, which is like by moving the stylus, you are kind of moving the tip of your robot. And this has its own set of problems. The second approach is we're trying to see what we can do with like a normal joypad. This does have other advantages, but also comes with its own set of problems. We also have issues with the control of the robots themselves. So then having a user control them when they're not that stable yet is enough. So this we are not able yet to answer, but it is, yeah, it's something we need in the next year to sort out for sure.
Okay, next is how much feedback does the robot need, and what kind of feedback mechanism will it use?
Yeah, so the robot itself doesn't need feedback in the sense that it has what we call proprioception. So the motors understand how much the tubes have been rotated, and it's then we know its state, and also you can see it through the microscope. We are developing sensors that are there to show you how far you are from the target or what forces you are applying, and I think this will be very useful for safe surgery.
And then the last question is, will you need to undergo animal trials before commercialization, or will cadaver trials be sufficient?
Yeah, that's a very good question. It's a big debate as well. Some people would say, no, you don't need to do animal trials because my risk assessment is so and so that we have factored in everything, and we should definitely be considerate of animal welfare and the 3 R's. But in practice, as far as I know, and I'm not an expert, MHRA does come back and ask for some sort of proof of the process on animal models. So from the theoretical standpoint, no, but from the gathering evidence standpoint, probably yes.
Well, it seems like there's a lot of interest and questions. I'm just conscious of time. Would you be happy for people to drop you an email if they have any more questions?
Yeah, of course. Yeah, of course. You have my details, definitely.
Amazing. Thank you. So thanks to everyone for coming along today and for all your amazing questions. If you'd like to hear any more disruptive ideas, then we do actually have one more event in the Festival of Disruptive Thinking, which is on the ethics of artificial intelligence. Nina's just popped a link to our website now in the chat box. We also have a newsletter which you can subscribe to, and that's probably the best way to find out about other events and opportunities like this. So thanks again, Christoph, and thanks everyone for coming. I hope you all have a lovely afternoon.
Thank you for hosting me, and feel free to reach out. Definitely happy to show you everything. Have a good rest of the day. Bye-bye.
Thank you. Bye, everyone.